Hello, my name is Rickard König and I'm CTO and co-founder of Ekkono Solutions. Econo provides an edge machine learning library for embedded applications. And in this session, I'm going to talk about how edge machine learning in embedded systems can enable decision support for IoT devices. At Econo, we say that we make connected things smart. And the focus is on things rather than the production of the things. And we say connected because being connected means that you already have sensors and are able to collect data. The applications we have made today range from predictive maintenance on heat exchangers, stone crushers and dehumidifiers to optimization of gas turbines and buildings. I will tell you much more on how we do machine learning with Econo in just a minute, but let me first give you the outline of this talk. First, I will tell you about Econo's and the Qt company's collaboration on how to bridge the gap between the data scientist and other embedded stakeholders. Next, I'll go into details about Econo's approach to machine learning. And spoiler, it's not the typical one. And how we deliver machine learning to embedded devices. With that said, we will be going into examples and use cases, starting off with predicting the remaining useful life of a stone crusher and finishing off with a customer use case where we personalize the care in respiratory medicine. Sounds like a long journey? Well, let's get started then. Developing cross-platform application today includes experts in the form of developers, UI and UX designers and project manager that must all work together to bring a product to market. Here, the Qt company delivers great value through its existing toolchain and Qt Creator and Qt Design Studio. However, no one has been able to miss the rise of AI and machine learning, which inevitably is affecting the development process by including yet another expert, the data scientist, into the team. It is here that Econo and the Qt company have started a collaboration to bridge the gap between the data scientist and the machine learning solution and the embedded application and the embedded stakeholders. Qt Design Studio already has plugins for design-related applications, including Adobe Photoshop and Apple Sketch. And this enables you to import artwork into the studio and in the same time generate reusable QML code. In this way, UI and UX engineers can do their work inside the design studio and then pass the code to the developers who can continue the work in Qt Creator to provide logic and integration code in the backend using C++. When ready, the whole application can be deployed across platforms on anything from desktops to MCUs, which is really great when you're working with IoT devices. What we have been working on together with the Qt company is to provide a new plugin, just like the one for Photoshop and Sketch, but for Econo's machine learning models. And the idea is the plugin should make it easy to import a model and hook it up to sensor and artwork within the design studio. When the final application is later compiled and deployed, the model and all necessary pre-processing steps is bundled with it and will be available cross-platform even on smaller MCUs. This is important since machine learning-based decision support systems really need an intuitive user interface to become accepted by users. In the cloud, this is typically not a problem since you have resources and can use any user interface that you like. But when you go to the edge and deploy edge machine learning on it, the devices become much more constrained, and this task of deploying your application become harder. And you will have hardware that is much more heterogeneous. And this is really where collaboration between the Qt company and Econo really shine. Qt Design Studio and Qt Creator makes it easy to rapidly create intuitive user interfaces and deploy them cross-platform, while Econo's Edge Machine Learning library provides very resource-efficient machine learning. And I guess you are all rather familiar with Qt's products, otherwise you wouldn't be here, right? But maybe you haven't heard about Ekkono yet. So let me tell you a little bit of our approach to machine learning so you understand how we fit into the puzzle. But let's start from the beginning and why traditional machine learning approaches sometimes struggles or even fails. Of course, there is not an either-or. Some use cases are better done with a centralized approach in the cloud, while others are more suited for a decentralized approach at the edge. And the traditional approaches is based on this assumption that we have a set or fleet of similar devices which we can learn from by analyzing their data. And they have something in common and they are similar. Let's say that we, for example, want to do range prediction based on the fuel consumption for a fleet of trucks. And at first glance, this sounds like a reasonable idea, but in reality, it's however not so easy. The trucks will be used in various environments and have different configuration. And the configuration will even change over time as parts are being replaced. And just by making it possible to collect all relevant data can often be a showstopper. On top of that, you might be dealing with a flaky or very limited internet connection, or that you're not allowed to send data to the cloud due to security or integrity reasons. In this situation, a decentralized approach using edge machine learning will really shine. By creating one model per device and training it on board the device itself, you don't need to send all the data to the cloud, and you don't need to explain how a device differs from another one. You don't even need to collect data explaining differences between devices and their environments. The challenge is, of course, to enable this machine learning on edge devices, since they are very resource constrained, and especially in terms of CPU and memory resources. And what we have seen is that a key to enabling edge machine learning is to do incremental learning, which differ a little bit from typical machine learning approaches by continuously training the model as data becomes available. Instead of training it once on a large previously collected dataset, you make incremental steps. So incremental learning is a slightly harder problem since we don't know which values we're going to see. But on the other hand, we can start making rough predictions directly based on what we know so far and continuously learn and improve the model along the way. And in the same time, the computations are distributed over time, which avoids computational bottlenecks. And because of this reason, incremental learning is really the key to edge machine learning if we're going to learn on the device and not just do inference. So again, even though Econo and this talk focus on edge machine learning, it's not an either-or. Some things are better done in the cloud and some things are better done on the device. If you have a homogeneous fleet of devices working in a controlled environment and you want to analyze and compare them in the cloud, that is a perfect option. But we have identified several situations, in addition to different environment and configuration, where the device itself is a better place to do the machine learning. And naturally, data volume is one of the first things that comes to mind. Because sometimes the amount of data generated from an IoT device results in design decision, limiting data to averages that might hide important nuances of the data. Imagine, for example, sampling vibration data 10,000 times per second for hundreds of assets. It's not really practical to send all that data to the cloud. But sending the average is not either an option, since it will hide all useful information. But moving the processing closer to the edge might be an effective way of solving that problem by processing all the data on the device and only sending the relevant KPIs to the cloud. And another problem is latency. It is perhaps not as obvious as data volume, but as soon as you want to control something in real time, the control system, including the machine learning model in this case, really needs to reside on the device to avoid problem with latency. And designing applications to run part of the analysis direct on the IoT device not only reduces the latency, but can also ensure that applications are not disrupted in case of limited or intermittent network connectivity. This can be very useful when applications are deployed in remote or moving situations where the network coverage is poor or even to reduce cost coming from expensive connectivity technologies like cellular networks. Another relevant and common factor is related to privacy and security, since data available on the IoT device can contain business-sensitive or private information. While an application might want to use this information to run complex analytics in the cloud, the ability to do so might be constrained. But with edge analytics, an application can make sure that sensitive data is processed on the device and never saved, and only the data that is compliant is sent to the cloud. And finally, by placing the machine learning on the device itself in this way, it becomes natural to learn the individual behavior for each device and create one machine learning model per device. And imagine, for example, that your robotic land mover could learn your garden instead of running around randomly, as they mostly do today. If they could be much more efficient by knowing where the grass grows faster and where it should not go when you're on vacation, since to make it stuck and so on. This is not possible today since you don't optimize it locally. But with edge machine learning, that becomes a possibility. So how does Econo fit into this picture? Well, as I mentioned before, Econo is a machine learning library that is designed to be used on the edge devices and in their embedded application. The runtimes that you use can be deployed on devices using C or C++, while the modeling and configuration of the models is done on a laptop or workstation using Python or C#. The core functionality of the library is really to make it easy to deploy machine learning on edge devices, and of course enabling incremental learning. Our definition of an edge device is that it's sensor close, which can be a motor controller, an HMI or PLC, or a gateway where one can see real-time sensor data. And for decision support system that we're speaking about today, it is of course devices in the interactive layer that are targeted, because you need an HMI display to do decision support. Anyway, most connected products have a number of sensor and actuators, but constrained capacity and memory. And this is why we need a purpose-built library to enable machine learning. And one thing that directly differs from a cloud approach is that data needs to be consumed in a streaming fashion. Due to memory constraints, it is not possible to first collect a large batch of data and then pre-process it. This means that all pre-processing steps, including normalization, calculation of lag, deltas, moving average, expression and whatnot, must be done on the fly. And if you want to enable incremental learning, the library should also support assembling not just the prediction instance, but also the training instance. It can also be a good idea to integrate the pre-processing steps within the model. Because if you do that, it becomes easier to change the model. Because machine learning models and the pre-processing are often updated as you learn more about the problem. And to avoid needing to recompile your embedded application to, for example, support a new pre-processing step or just another version of your model, it is crucial that the library supports hot swapping of models. And then you need to have an integrated pipeline within the model. So you always just send the raw sensor data to the model. In this way, the data scientist can continuously work on improving the model without changing the embedded application. A sort of separation of concern, which is a good pattern in all software development. In this slide, you see an example of the few lines of code that would be needed in an application to load and execute an arbitrary machine learning model, given an integrated pipeline for pre-processing. It doesn't need to be more complex than that, and this makes it easy to change and try out new models if you want that. So, to sum up, Econo provides an efficient machine learning library, purpose-built for edge machine learning. This means that you get an efficient execution of the machine learning in your application while requiring minimal new code. It is in this way that the integration in Qt Design Studio is made possible, because when you import a model using the plugin, you not only get the model itself, but all the pre-processing, normalization, and the possibility to apply incremental training on the device. So you can actually continue to learn on the device. With all that out of the way, let's get down to some real examples and also use cases that demonstrate the power of this decentralized edge machine learning. Let's start with an example. Imagine that we have a heavy piece of machinery with some wear parts that is gradually worn down. Here we'll take the example of a stone crusher, which is used in mines and on construction sites. Naturally, the crusher is under heavy wear, and the mantle that the stone are crushed against gradually is worn down and eventually needs to replace, which is a quite time-consuming procedure. However, the frequency for how often the mantle needs to be replaced depends on the hardness or the density of the material it is crushing and how hard the machine is run. The density of the material differs between sites and even over time at the same site and cannot be measured in a practical way. Here it becomes interesting, and a centralized approach would struggle since the wear would differ greatly among sites and we can't measure it. We have full control of the operation of the machine and the power it uses, but we cannot estimate the density of the material and thereby the wear. But let's assume that we now have 4 sites, A, B, C and D, which all have different stone materials. And the charts that you see here then show how the wear in dark green, defined as the remaining mantle thickness, varies among the sites depending on the density of the crushed material, depicted in orange, and the current power usage, depicted in red. Note that the density fluctuates and that the mantle used in site A lasts almost twice the time compared to site C. Now let's look at how we would tackle this problem with a centralized approach. First of all, we would need to upload all the data related to the wear and power consumption to the cloud for each site. This is often easier said than done, especially from remote mining sites. But let's say that we have been able to upload the data to the cloud. Then the next step is to build a model that can predict how much time and power we can still use a particular machine before the mantle needs to replace. So the total power usage which is left relates to the time that you can use it, depending on how hard you run it. But here we run into problems since the density of the material varies between the sites and since we cannot measure it. Thus, there is no way to account for the wear in the cloud, and the best we can do is to estimate an average wear, given that we have previously gathered statistics on that is. So, if we do that and look at these charts again, and again we see the wear as the dark green line. But here the red line depicts the accumulated power used over time. And finally, the light green horizontal line is the prediction of the total power consumption that the centralized model would give. That is, the observed average of the previously changed mantles. So, if the prediction, the light green line, and the accumulated power consumption meet at the same point, when the wear reaches 0, the prediction is perfect. And that is, the predicted total power you can get out of a mantle has a perfect correlation with the actual power consumption and time that you got from that mantle. Looking at the chart, we can see that the prediction is rather good for site B and site C, while site A could run much longer than predicted and site D significantly shorter, which is even worse. Obviously, this is not a good solution, and we would like to have an individual prediction for each of them. So then, if we instead turn to the decentralized edge machine learning approach, we would instead construct one model per crusher. And the model would consume the sensor reading and make a prediction without needing to communicate the raw data to the cloud. And we would, by using incremental learning, avoid the need to first collect a large data set or gather statistics, while also enabling adaptation of the model if the crusher would be moved to a new site or if the density of the material would change. so that becomes a much more flexible and effective solution. And if we look at these charts, we see that the result of applying the decentralized approach for the same problem. And here again, the light green line is the predicted total power consumption, and the red line is the actual accumulated power consumption. First, we can note that the error between the predicted total power consumption and the actual accumulated consumption is almost zero. And secondly, the prediction is no longer a horizontal straight line, but varies over time, which is due to the incremental learning and the data it sees. The prediction fluctuates the most in the beginning, since the model then has seen the fewest data points, and they themselves contain both noise and variation. However, it only takes around 100 data points until the model finds a general pattern and the prediction is stabilized. So in the last half of the mental life, where actually an accurate prediction is most important, the predictions are both stable and very accurate. So even if we don't know the conditions of the stone at each site, we can still make the accurate predictions since it's not changing. But what would happen if a change in stone density occurred during the life of the mantle? Maybe because you reach another sediment in the mountain. Well, let's assume that a change to a much higher density of the material does occur due to a change of location or material then, as depicted in the charts for site E and F. And it's easy to see that the higher density affects the wear, as it gives the light green wear line a much steeper angle after the change. However, since we're using the incremental learning and continuously adapting, the model automatically accounts for the change. Naturally, it's not possible to predict the shorter lifetime beforehand, since the change was unknown, but after only a few data points, the model has been retrained and gives a much more accurate prediction again. Okay, so that was an example, and now let's look at a real customer use case that we started in August this year with the British medtech company Peninsula Medical Technology, or PenMed. They focus on the field of critical care and anesthesia with the development of an anesthesia machine and ICU ventilator. With the rise of COVID, the need to speed up the development of modern emergency care has never been more pressing, and they came to Ekkono to bring smart technology into the development phase. PenMed combines the experience and expertise of clinical end users and the power of machine learning. In this case, they wanted to explore Econo's add-on to the Qt Design Studio to get a new approach for optimizing the treatment of patients in emergency care using machine learning. When PenMed presented the idea of smart and more personalized approach using edge machine learning, we tailored the machine learning solution even more with our unique incremental learning method. It's really the same approach we just looked at with the stone crusher, but applied to patients and ventilators. The project is still ongoing, but the results so far are groundbreaking, and the plan is to get the product to market as fast as possible. The collaboration between PenMed, Econo and the Qt company has been vital for the success of the project, since visual inspection is required by the doctors, and since the machine learning has to be done on the device to ensure fast response time without the risk of interference. Or as Dr. Sebastian Brown at PenMed stated, a key for doctors to accept machine learning in life supporting system is to offer an intuitive way to visualize the data. That's why the combination of Qt and Econo is the perfect fit for us. So, what have we learned? Well, the point of this example was to demonstrate how decentralized edge machine learning can solve problems that a traditional centralized machine learning approach cannot. We saw, for example, that environmental factors that differ between devices can be ignored if we create one model per device. And even when a new model was trained from scratch, it was significantly more accurate than a centralized approach, and very accurate at the end of the lifetime of the device, where it mattered the most. We also saw that incremental learning enables adaptation to changes in the environment. And the approach taken here holds for most applications of remaining useful life, where individual usage or environmental factors affect the life of the device. It also extends to most predictive maintenance use cases and even optimization that must be done on an individual level. And it's interesting to think about that until today, a product has been at its best when it has left the factory. But with incremental learning and on the edge, they can become better and more optimized for their specific usage the longer they are used. And the key is to divide the problem into smaller parts by making one model per device, and to use incremental learning to adapt to changes and to make it feasible to run the machine learning on the device themselves. And finally, the collaboration between Econo and the Qt company aims to handle the added complexity of bringing machine learning into your embedded application, while enabling efficient cross-platform deployment with intuitive user interfaces. The plugin makes it very simple and straightforward to import an Econo model, hook it up to sensors in the UI in the Qt Design Studio, and deploy it cross-platform. This is a good step towards speeding up the development of embedded applications that rely on machine learning. So that was all. Thank you for your attention. And if you have any more questions, we can continue the discussion in the speakers lounge. I will be there for the next 30 minutes at least. Thank you so much.